Hey everyone, welcome to this explainer. Today, we're not just staring at dry math or some abstract equations scribbled on a whiteboard. No way. We are actually going to explore the underlying architectural language of truth and computing itself. We're going to decode predicate logic. Honestly, think of it as the ultimate blueprint for structuring undeniable facts. So get ready, because we are going to build this logic step by step, right from the ground up.
Here's our roadmap for today. We'll start with the architecture of logic, lay our foundation with predicates, and establish scope using quantifiers. Then we'll tackle the rules of negation and wrap the whole shebang up with free versus bound variables.
Okay, let's dive right into this. Part 1. The architecture of logic. So, how exactly do we take the messy, complicated ways we humans communicate and translate them into something a machine or, a mathematical proof can actually understand? Think of this entire explainer as your personal translation guide. Human language is full of ambiguity, nuance, and poetry, and hey, that's beautiful for art, but it's absolutely terrible for proving absolute truth or, say, programming a database search. Humans are beautifully nuanced, but machines, they are incredibly literal and, let's face it, pretty stubborn. We need a bridge between our abstract human ideas and a rigid, flawless logical architecture. Predicate logic provides exactly that bridge. It gives us a structural truth that we can rely on without question, literally powering the algorithms and AI logic that run our digital world.
Moving on to part 2, the foundation, which is all about predicates.
Let me introduce you to the main character of our logical language, the predicate. Simply put, a predicate is a function that returns a truth value. At its absolute heart, you can think of a predicate as a little processing machine. You feed a piece of information into this machine, it runs its check, and it spits out exactly one of two answers: true or false. There's no maybe, no sometimes, and absolutely no gray area. It is a strict, binary truth engine.
Let's ground this abstract idea with a super concrete example. Let's say P of x represents the statement x is even. We're actually going to use this specific anchor example throughout this entire explainer just to make all these complex rules much easier to digest. So P is our predicate, our little machine checking for evenness, and x is whatever number we decide to feed into it. If we feed a 4 into P of x, the machine happily spits out true. If we feed a 5 into it, the machine spits out false. That simple, elegant mechanism is the bedrock of our entire logical language.
That brings us to part 3, the scope, handled by quantifiers. Now, you might be wondering, since we have our single-use predicates, how on earth do we apply them to massive groups of things without testing them one by one? Well, we need a grammar system to govern our new vocabulary, and we manage this using quantifiers. Quantifiers are symbols that define the scope or the scale of a predicate. They are the absolutely crucial tools that tell us exactly how many things our little true-false machine applies to in a given universe. Are we talking about every single thing, or just a few things?
Now, what's really interesting about this is the stark visual contrast between the two dominant symbols of scale in predicate logic. We have the universal quantifier, which is represented by a bold upside-down A, and then we have the existential quantifier, represented by a backwards E. These two distinct symbols dictate the entire reach and power of our logical statements.
Let's break down the universal quantifier first. When you see that upside-down A next to an x, followed by our predicate P of x, it perfectly translates to this phrase: for all x, P of x. Using our anchor example, this formula boldly claims, for all x, x is even. It's an absolute, sweeping statement applying to every single item in whatever numerical universe we're currently evaluating.
Now contrast that massive scope with the existential quantifier. When you see that backwards E, the formula translates to, there exists an x such that P of x. This dramatically scales down the claim. Instead of claiming something about everything, we're now just looking for a minimum of 1. In our example, it means there exists at least one x that is even. It doesn't mean they all are, it just guarantees that somewhere out there, at least one matches our predicate.
Let's move to part 4 and see how this builds, the rules of negation. So, we know how to state things positively and scale them up, right? But how do we mathematically express logical opposites? Take a second and ponder this question. If someone makes a massive universal claim, how do we mathematically prove that universal rule is false? Think about it. If a formula claims every single number is even, you don't need to check infinity to prove them wrong. You just need to find one single number that isn't even. That intuitive, everyday logic translates into a beautiful mathematical symmetry.
Here's exactly how that symmetry looks. The symbol on the outside is a negation, a mathematical not. So the first part says, not all x have the property P.
What's the exact mathematical equivalent to that? Well, the other side tells us there exists an x that does not have the property p. Let's use our anchor again. Saying not all x are even is exactly, perfectly the same as saying there exists an x that is not even. Pretty cool, right?
Now let's look at the inverse rule. What happens when we negate an existential claim? One side says it is not the case that there exists an x with property p. Or, simply put, there does not exist an x that is even. That is perfectly equivalent to saying, for all x, x is not even. Make sense? If none exist, then absolutely all of them are not.
So the absolutely crucial point here is the visual and mechanical symmetry of how this operation works. When you want to negate a quantified statement, you just follow 3 simple steps. First, you pass the negation symbol through the parentheses. Second, as it passes through, it elegantly flips the quantifier to its opposite, so universal becomes existential, and existential becomes universal. And finally, the negation lands directly on the underlying predicate itself. It's a beautifully consistent, foolproof rule. Finally, Part 5, Free versus Bound Variables. This is the final grammatical rule we need to understand the anatomy and legal status of the variables themselves within our architecture. You see, in predicate logic, an x isn't just a letter. It has a specific status based strictly on where it lives in the formula. Variables that are safely captured inside a quantifier's scope, meaning they have an a or an e explicitly governing them, are what we call bound. They are tied to that specific logical rule. On the flip side, variables that are left outside, without a quantifier explicitly claiming them, are completely free. Understanding whether a variable is free or bound is critical because it tells us whether our statement is a complete, verifiable fact or if it still has open slots waiting for definitions. And this matters immensely in the real world because a computer simply cannot process an open slot. It needs bound, verifiable facts to successfully run a program or query a database.
By putting all of these pieces together, we're doing so much more than just memorizing a few math symbols. We are literally mastering the architecture of logical thought itself. By mastering just these few elements, the binary truth of predicates, the grand scope of quantifiers, and the strict rules governing variables and negation, we gain the immense power to formalize absolute truth. We can take complex conditions and lock them into airtight, irrefutable structures.
We started this explainer by recognizing the messy ambiguity of human communication, but now you possess a rigid structural translation tool. So I'm going to leave you with this provocative thought to ponder. If human language is so full of ambiguity, what else in our chaotic real world can we translate into the absolute, undeniable certainty of predicate logic? Keep looking for those structures in everything you read, argue, and say. Thank you so much for joining me, and keep exploring.